That I wanted to show you in class on Thursday. It involves a wheel that's rolling up this hill, and because it's rolling, there must be friction between the wheel and the hill. And I for the wheel is going to be 1/2 mr squared, where m is the mass of the wheel and r is the radius. And it's getting slower, and I'd like to know what its acceleration is. And we can set this up using Newton's second law, but we are going to need a force diagram. So, a force diagram for the actual object includes gravity pointing down and our normal force perpendicular, and the friction force pointing up, as we talked about in class. It's a static friction. I'm just going to leave it as F because I'm against writing subscripts at this particular hour. We also need to consider the torques acting too, because it's a wheel. And we talked about in class that the axis of rotation being in the center, the gravity force contributes no torque. And the normal force acts through that rotational axis, so it also causes no torque. I'm going to put the official sign of no torque, which is a yellow X. It's not really the official sign, but I think you get the picture. But we do have that friction force that can cause a torque. So starting over here with net torque equals I alpha, the net torque is just going to be R times F. Remember, torque is RF sine theta, and since the sine of 90 is going to be 1, we just have R times that friction force F. And the moment of inertia, that's going to be 1/2 mr squared. And then we have times alpha. And since it's rolling, we can say that the acceleration is equal to r alpha. This is an equation that we can use for objects that undergo rolling motion. Same thing with v equals r omega. The center of mass motion is tied into the rotational motion with these math models. So I'm going to rewrite alpha as a over r. And when we do that, we get some fantastic canceling that goes on here. I think you'll see that all the r's end up going away. And we're going to be left with this equation, which I'll write in yellow, because why not? That F, the friction force, must be equal to 1/2 mass times acceleration. So we don't know what the friction force is. And one of the things I said in class was that let's assume the maximum static friction force, which is not a valid or good assumption. We don't know what the friction force is. And that's okay, because we have two unknowns, and we have a whole other set of Newton's laws, Newton's second law problem over here that we can use to set this up and get the same two unknowns. So if we look along the axis that it's accelerating, where that's our angle theta, along the acceleration axis, the net force can be written. So the net force, and I'll make down the ramp positive. It's arbitrary, but if I make down the ramp positive, then we have Fg sine theta minus the friction force equals ma. And I can do our usual substitution of mg and then I can do the thing here where I don't know what the friction force is, but I have an expression for it that includes acceleration. So that's going to get plugged in over here for the friction force. So when I make that substitution, mg sine theta, and then minus 1/2 ma equals ma. Aha! And this looks very solvable for acceleration. And I can get rid of the masses in all three of these. So at that point I have g sine theta minus 1/2 of a equals a. Adding 1/2 of a to both sides gives me g sine theta. And then 1/2 plus 1 is 3/2. And then solving for acceleration, finally, we end up with 2/3 g sine theta. That is the expression for the acceleration. And notice if there were no friction, the acceleration would be just g sine theta. like we've seen before with a frictionless block sliding up and down an incline. So adding the rotation makes this 2/3 term pop into the acceleration equation.